Okay, we've gone through the solar system. Now we're here at Earth. The first thing we hit is the magnetic field. It is like as if there was a dipolar magnet in the center of the Earth with a north end and a south end. Uh, we wouldn't be here if it weren't for the Earth's magnetic field. It's generated in the liquid outer core of the Earth. The beauty of the magnetic field is it deflects solar wind. And so we have this lens-shaped, teardrop-shaped magnetic field lines that go away from the sun. And at the end of the sun, it's kind of rounded. On the edges are the Van Allen belts, and the Van Allen belts are what really protect us from that solar wind. If we didn't have the protection of the magnetic field, we would just get burned up by the solar wind. The Van Allen belts, though, some solar wind can get through the Van Allen belts, and that's when we have the aurora borealis in the north, and in the southern hemisphere, the aurora australis. So this is where some of that solar wind does get into the Earth's atmosphere. All right, plunging through the atmosphere. Let me just turn my face off. Plunging through the atmosphere. To note is that the atmosphere on Earth is mostly nitrogen. Look at this graph, circle graph here, pie chart, pie graph. 78% nitrogen, 20.9% oxygen, and then just 1% other gases. So there's not a lot of other gases by percent. The other gases are those like argon, carbon dioxide, neon, methane, ozone, carbon monoxide, and sulfur dioxide. So mostly we have a nitrogen-rich atmosphere. The atmosphere, we'll go back, of Earth has changed over time. So it's really been kind of three atmospheres. The early atmosphere was a hydrogen-helium atmosphere just after the Big Bang and the solar system forming. That helium hydrogen atmosphere, though, was really hot, and a lot of molecular activity, and it blew away with the solar wind. The next atmosphere for the Earth was generated by the volcanoes, those volcanic gases, those sulfur dioxides, nitrous gases, carbon dioxide, and water vapor. As the Earth cooled down, then some of that water vapor was able to condense until we had water on Earth. But it wasn't until like the cyanobacterias, like and algae formed, that we started to get a atmosphere that was almost 21% oxygen. So that came later. The atmosphere in other planets is also pretty different than ours, obviously. There's me again. The Earth's atmosphere, you can see through it. You can see if from space, you can see our continents and our oceans and the clouds. Venus has a really dense, murky atmosphere. We can't see the surface of it. And then planets like Mars have a really low density atmosphere. Okay, our atmosphere, I move my head out of the way. Because of gravity, molecules are pulled closer to the Earth, and so the atmosphere closer to the Earth is denser than it is further away. That's all due to gravity. Because of the density of those molecules, then we have a higher pressure here at the Earth's surface. It's 14.7 pounds per square inch. As you go further away, then that pressure decreases. And here, 1 bar is 14.7. So it decreases as you go up, up, up. Here's Mount Everest, and continues to decrease. The ability for that air to hold heat then also decreases, so it gets colder as you go up. Okay. Here is a graph showing the different layers of the Earth. The atmospheres are separated what's called pauses. So the top of the troposphere is the tropopause, top of the stratosphere is the stratopause, and so on. You can see the pauses names in here. Closest to the Earth is the troposphere, and that's about 11 kilometers thick. It's the area where the weather is, so there's lots of mixing. It does cool, the Earth radiates heat and it does cool as the elevation rises. You get to the stratosphere, and in here there's not so much mixing. There's not weather, and the temperature gets steady and then increases because the ozone, O3, ozone absorbs heat. Then you get to the stratopause and you're at the mesosphere. The mesosphere, there's losing heat. There's nothing, it's low density, it just loses heat. And then up to the thermosphere, heat increases again because of the absorption of solar energy.